Threads versus processes. Hello guys, I'm coming from the future. I recorded this video before. This video is the second half of the video about threads versus processes, but you can watch independently from the first part. I will add the first part at the end of this video. In this session, we will talk about context switching, deadlocks, and other important elements of thread versus processes. Enjoy watching the video. Now let's talk about context switching, because this is where things quietly become catastrophic. A CPU core can only execute one thread at a time. So if you create thousands of threads, the operating system constantly pauses one thread and resumes another. That operation is called context switch, and context switches are not free. The CPU has to save thread state, load another one, update scheduling metadata, and continue execution. But the deeper cost is cache disruption. Modern CPUs are fast because they keep frequently used data extremely close inside caches, like layer 1, layer 2, or layer 3 caches. If you want to know about CPU caches, you may watch this video. We'll not go through the technical discussions for cache. But in our example, if thread A and thread B constantly working on different memory regions, those caches become much less useful. Now CPU has to wait on RAM instead, and RAM is catastrophically slow compared to CPU speed. So when you add too many threads, your program may spend more time on switching or waiting or locking or waking, and even reloading the caches. And this makes it more busy than doing actual useful work. That is why more threads is not automatically a performance strategy. It's a resource decision, and every programmer eventually experiences this moment. You write a multi-threaded version, you are so excited and happy, you run it, it's slower. So you add more threads, but the results get even slower. Your CPU graph looks impressive, your laptop fan spins like a hell, but the actual work barely moves. The problem is not that threads are bad. The problem is that threads are workers sharing the same kitchen, same stove, same knife, same cutting board. And if every worker keeps yelling, "Move, I need the mutex," dinner doesn't arrive faster. Now there is another problem, deadlocks. Thread A holds like A, and once like B. Thread B holds like B, and once like A. Nobody moves. The program is not slow anymore. It's dead. And this is why high-performance systems try to reduce shared mutable state as much as possible. Because the fastest lock is not the lock you never needed. This needs to be one of the most important parallel programming patterns. Split the work into independent chunks. Let workers operate independently. Combine the results later. Instead of 8 threads fighting over one shared counter, give each thread its own local counter and merge the results at the end. Much less contention, much less waiting. But even here, there is another hidden trap, false sharing. 2 threads modify different variables, but those variables happen to live on the same CPU cache line. So the CPU cores keep invalidating each other's cache entries, even though the variables are logically separate. No shared variables in your code, but shared hardware underneath. And this is why performance engineering becomes so difficult. By the way, if you're curious and you want to learn more about fault sharing, you may watch this video. The performance engineering is difficult because sometimes the bottleneck is not visible in your algorithm. It's hidden inside hardware itself. Now let's simplify the big picture. Threads are useful when tasks spend time waiting. Processes are useful when tasks spend time calculating. Threads share memory easily. Processes isolate memory safely. Threads are lightweight. Processes are heavier. Neither is universally better. The correct answer depends entirely on the workload. And that leads to the single most important question in performance engineering. What is the bottleneck? Because if your program is waiting on disk, adding CPU threads may do nothing. If your program is waiting on a database, more cores may do nothing. If your program is lock-bound, more thread may actually make it worse. And if your Python code is CPU-bound in a standard C Python, threads may never give through parallel execution in the first place. So before adding threads, you need to measure your program. Don't guess, use a profiler, because performance is not a belief system, it's evidence. Now is a good time to talk about async, because people often mix these ideas together. Async is usually concurrency inside a single thread. Tasks voluntarily pause while waiting so another task can run. That's fantastic for handling huge numbers of network requests. But async does not magically make CPU-heavy code parallel. If you are building a web crawler, async can be amazing. If you're compressing video, async is not your hero. You need to use the right tool for that workload. Now let's return to our discussion. Why can more threads make your code slower? Because every thread adds overhead, because synchronization catches waiting, because locks serialize execution, because context switching disrupts caches, and because memory bandwidth is finite. Some workloads simply do not parallelize efficiently, and some parts of a program are fundamentally serial. The idea has a name, Amdahl's law. Even if most of your program parallelizes perfectly, the serial portion limits the maximum speedup. Infinite threads do not create infinite performance. Reality always wins. So if someone says, we'll just add more threads, your first response should not be great idea. It should be what exactly is the bottleneck. Because once you understand where time actually goes, performance is not magic anymore. It is an engineering task under your hand. And engineering is better than magic. At least in this case. Maybe engineering is magic. I don't know. It's your interpretation. Engineering gives you a profiler. So the next time your code is slow and you feel that you need to add more threads, pause for a second. Ask yourself what the threads actually do, what they will share, what they will wait for, or whether they will truly run in parallel, and whether the overhead is even worth it. Because sometimes one thread really is too slow, but sometimes 8 threads are just one bottleneck with 7 witnesses. And that is why more threads can make your code slower. This is ML Guy, and together we'll go deep to understand the systems under the hood. Until the next video, good morning, good afternoon, and good evening. Bye.